Universal law of gravitation. Know that the rings of Saturn, which appear so solid, are not really rings at all. They consist of countless chunks of ice and rocks, ranging in size from enormously large to tiny grains of sand, each circling the planet in its own individual orbit. The force that created and preserved the rings is the same force that binds us to the Earth's surface, that is, gravitation. Since ancient times, observation of stars, planets and their motion have been the subject of attention in many countries. The biggest milestone in this endeavor was the discovery of universal law of gravitation by Newton in 1686. With just one simple equation, he described the force of gravity and showed that the same law of gravity is also applicable to the moon and to other astronomical objects. Newton also determined the orbits of planets, moons and comets. About 2000 years ago, Greek philosopher Ptolemy proposed Geocentric Model, according to which all celestial bodies, including the stars, the sun and the planets, revolved in circular orbits, and the Earth was at the center. In 1543, a Polish monk, Nicolas Copernicus, proposed a different model, according to which all the planets moved in circles with the sun at the center. That is known as Heliocentric Model. However, a more elegant model in which the sun was at the center around which all planets revolved was already mentioned by Aryabhatta in the 5th century AD. German mathematician and astronomer Johannes Kepler formulated 3 laws of planetary motion, also known as Kepler's law of planetary motion. He realized that Copernicus' concept of circular orbits about the sun had to be abandoned. To Kepler's first law of planetary motion, planets move around the sun in the elliptical orbits, that is, flattened circles with the sun at one of its focus. This is also known as law of orbits. According to his second law of planetary motion, also known as law of areas, line connecting the sun to a planet sweeps equal areas in equal times. If A1 is the area swept by a planet in a given period of time near one focus, and A2 is the area swept by the planet in the same period of time near another focus, then the planet swept equal areas. The importance of Kepler's second law is that though the orbit is symmetric, but the motion is not. A planet speeds up when it is approaching the sun, gets its greatest velocity when passing closest to the sun, and speeds down when it is moving away from the sun, and gets its lowest velocity when passing at the farthest point from the sun. According to Kepler's third law of planetary motion, also known as law of periods, the square of the orbital period of a planet is proportional to the cube of its mean distance from the sun, which is half the sum of the smallest and the greatest distance from the sun. It has been said that Newton was struck on the head by a falling apple while sleeping under a tree. This accident was considered to inspire him to predict that perhaps all bodies in the universe are attracted to each other, and so was the apple attracted to the earth. Newton then analyzed the motion of the moon around the earth and concluded that the force governing the motion of the moon is same as the force that attracts a falling apple to the earth, that is, the gravitational force. He further concluded that similar to the Earth-Moon system, a gravitational force causes the motion of the planets around the Sun. He proposed his law of gravitation, according to which every particle in the universe attracts every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. If the 2-point masses A and B of masses m1 and m2 are at a distance r from each other, then, according to the law of gravitation, the force of attraction on point mass B due to another point mass A is proportional to the product of their masses and inversely proportional to the square of the distance between them. Hence, the magnitude of the force is proportional to the product of the two masses upon the square of the distance between them, or the magnitude of the force is equal to g times the product of the two masses upon the square of the distance between them, where g is the proportionality constant known as universal gravitational constant. Direction of the force is towards the point mass A. The force law given by Newton is often referred to as inverse square law because the magnitude of the force varies as the inverse square of the separation of the point masses. The same can be verified by varying the separation between the two masses. The law of gravitation applies only to the point masses in which the entire mass of a point mass is supposed to be concentrated at a point. Symmetrical bodies, such as a sphere having uniform density, can also be considered as point mass, as their masses are also concentrated at the centers. In such cases, distance r is the separation between their centers. In formulating his law of gravitation, Newton used the following observations. For the circular motion of an object, a net force, that is, the centripetal force, had to be acting on the object because, without such a force, it would move in a straight line path rather than in a circular path. For example, if we tie a stone at the end of a string and whirl it around a circle as the stone moves, direction of its velocity changes continuously. That indicates it has acceleration. According to Newton's second law of motion, a force is the cause of an accelerated motion. Since the string can only pull the stone, therefore, the force exerted by the string is towards the center of the circle. And if we leave the string, it will become loose. It will no longer pull the stone, and the stone will move away along a tangent to the circular path. The pulling force required to move an object in a circular path is also called the centripetal force, and the corresponding acceleration is called centripetal acceleration. If an object of mass m moves with a uniform speed v along a circular path of radius r, then its centripetal acceleration can be measured as v square upon r, thereby its centripetal force can be measured as mv square upon r. It moves around the Sun in an elliptical orbit, but in most of the cases it is very close to the circle. Therefore, Newton considered the orbit to be circular and measured the centripetal force, that is, the gravitational force that the Sun exerts on a planet when the planet moves around it. By knowing the total distance covered by the planet around the Sun, that is, the circumference of its orbit and its orbital time period, orbital velocity of the planet can be measured as 2 pi r upon t. Hence, centripetal acceleration due to Sun's gravity, A, comes out as 4 pi square r upon t square. And the corresponding centripetal force becomes 4 pi square m r upon t square. If two planets of masses m1 and m2 are separated from the Sun by the distances r1 and r2 respectively, then the gravitational forces exerted by the Sun on them are 4 pi square m1 r1 upon t1 square and 4 pi square m2 r2 upon t2 square, respectively. And the ratio of the two forces becomes m1 r1 t2 square upon m2 r2 t1 square. According to the Kepler's third law of planetary motion, square of the orbital period of a planet is proportional to the cube of the mean distance from the Sun. Hence, this ratio can be rewritten as m1 r2 square upon m2 r1 square. That is, the force responsible for the planetary motion is proportional to the mass of the planet and inversely proportional to the square of the distance of the planet from the Sun. According to Newton's third law of motion, a force of the same magnitude must be exerted on the Sun by the planet. If the force is proportional to the mass of the planet, then it should also be proportional to the mass of the Sun as well. Thereby, the gravitational force exerted by the Sun on a planet is equal to g times the product of the masses of the Sun and the planet upon the square of the distance between their centers, where g is the universal gravitational constant. In 1798, British scientist Henry Cavendish experimentally measured the value of g, which is equal to 6.67 into 10 to power minus 11 Newton meter square per kilogram square. If 2 point masses, each of mass 1 kg, are separated by a distance of 1 meter, then, according to the Newton's law of gravitation, the force of attraction between the masses becomes equal to the universal gravitational constant g. It has been found that this force is equal to 6.67 into 10 to power minus 11 newtons. Hence, the value of g should be 6.67 into 10 to power minus 11 Newton meter square per kilogram square. Knowing the value of g, one can determine the masses of Sun, Earth, Moon and other planets. Let us see how. For a planet like the Earth, moving in a circular orbit around the Sun, the necessary centripetal force is provided by the gravitational force of attraction. Therefore, g into m upon r square must be equal to 4 pi square into mr upon t square. By rearranging, mass of the Sun can be obtained by the relation 4 pi square r cube upon gt square. By substituting the values of g, orbital time period of the Earth and the mean Sun-Earth distance, we can measure the mass of the Sun. That comes out to be 1.98 into 10 to the power 30 kg. In the similar way, by knowing the orbital period of the Moon and the mean Earth-Moon distance, one can find the mass of the Earth. Let us measure the force of attraction between Earth and a stone of mass 2 kg placed on the Earth's surface. Force of attraction between the Earth and the stone can be obtained by substituting the values of g, mass of the Earth, mass of the stone, and the distance of the stone from the Earth's center, that is, the radius of the Earth in the given relation. The gravitational force comes out to be 19.6 newtons. On the other hand, if the two masses each of mass 2 kg are separated by a distance of 1 meter, then the force of gravitation between them comes out to be 2.7 into 10 to the power minus 10 newtons, which is very, very small as compared to the force exerted by the Earth. Today, Newton's law of gravitation is used to determine the orbits that take spacecrafts from the Earth to various destinations within our solar system and beyond. In addition, law allows us to calculate with pinpoint accuracy of the time of solar eclipses and other astronomical events.